Okay.
We're rolling.
Hello, everyone. Welcome back to another session of the Learning Glass Studio. And today we'll talk about thermodynamics of materials. And so phase diagrams are a very important part of the materials world and other applications of phase diagrams, which is a property of thermodynamics. I mean, you build the phase diagrams based on thermodynamic principles, and they're very useful and very powerful. Specifically for materials, binary alloys is one application of phase diagrams, and of course binary means two different metals that are form a material, and when everything is stable, they can form a solid solution to give you specific material properties. So the phase diagram is pretty much a starting point to help to understand how to work with these materials, form these materials, and know when they work or not in terms of stability, basically. So to start off, we'll talk about a single compound, the water phase diagram, which we may be familiar with, that this is one molecule. It's not binary, but to start off, we'll start with a singular, unitary, whatever you want to call that, single, solo. So as a function of temperature and pressure, we can talk about phases. So in solid and materials, phases are also applied, but most of the time when we talk about material phases, we're talking about a solid that the atomic and molecular and microstructure are arranged in a certain pattern. And each different pattern or structure is a phase. So that is also what phase diagrams are keeping track of. And to extend that concept, phases also extend into the fact that this matter, this mixture can be gas phase, this mixture can be a liquid phase. So as we know from the case of water, H2O molecule, depending on the pressure and depending on the temperature, you can get a solid, liquid, or a vapor. So as we're familiar with, we know we can have some intuition on, and the Celsius temperature scale is based on the fact that water has different phase changes at some certain landmark temperatures that this scale is based on. So 0 Celsius is a nice convenient thing that us humans have a nice convenient, I guess all life on Earth has a convenient familiarity with, that at 0 Celsius, water freezes. At 100 Celsius, water boils. At 1 atmosphere, as long as you're at this, some ambient pressure that's defined. So I'm going to draw like miles, hallmark, or very important markers of this phase diagram for water. So that's 100 PA, that's not 1 atmosphere. 100 kilopascals is 1 atmosphere-ish, close. 1 bar is 100 kilopascals, which is very close to 1 atmosphere. It's like 1% difference. So these are some useful benchmarks of the behavior of water. At 1 atmosphere, 100 kPa, and 0 Celsius, that's where water freezes. At 1 atmosphere, 100 Celsius, that's where water boils, meaning the transition from solid to liquid, or liquid to solid, the transition from liquid to gas, or gas to liquid. That's what boiling and freezing mean. And there's another parameter which is unique to many, I think all material systems. One is called the triple point, and then if we go over here into the high pressure, high temperature regime, we have something called the critical point. So if you go to higher temperatures, lower pressure, then you can draw a boundary. So this line will be all boiling points between liquid water and vapor water, gas phase water. And at one atmosphere, that boundary is at 100 Celsius. But if you increase the pressure, you need higher and higher temperatures to boil it. As you decrease the pressure, you need lower and lower pressure temperatures to boil. So that all depends on the phase. This is the phase diagram. It's the thermodynamic behavior. So there's some properties of the material, in this case water, that determine the phase changes and the stability. So to complete this diagram here, there's another boundary where it depends on the pressure. I mean, it doesn't depend, the dependence of freezing does not depend as much on pressure as this boundary does. So this would be the solid. So that's a phase diagram of water. And what it's based on is thermodynamic properties. Those being internal energy. Another way of quantifying internal energy is enthalpy, which is more useful in many cases. Entropy, which is different than internal energy. It has to do more with some probability of molecular arrangements and configurations and statistics, or more simply, which is less accurate though, is disorder. So that's another thermodynamic parameter. And a very powerful thermodynamic parameter is Gibbs free energy, which is a combination by its root definition. By definition, that's what this three equal sign equals. It's the competition between enthalpy and entropy, or internal energy and entropy. And it also determines equilibrium. It determines thermodynamic equilibrium. For both either a chemical reaction or a phase change. So it determines equilibrium among phases or chemistry reactions, a conversion between one molecule and another molecule through some chemical process. So for any process where you have, just in general, this is not mathematically general, but it's just a symbolic, quick way to think about it, is if you start with something A, it can be either some molecule or some phase going to some process from A to B, you can define the Gibbs free energy change. Gibbs free energy change from A to B as final minus initial. So if we're saying it goes this direction, the final state would be B and the final state of A. So if you can, there's ways to come up with these numbers. There's measurements and some theory, but the idea with thermodynamics is you can define these free energies, and the way that you use it is if the number you get is greater than 0, then the starting position. So you're saying this is final minus initial. If this number is greater than 0, then A is favored thermodynamically. It's a thermodynamic favor. If it equals to 0, then that means you're at some equilibrium. Some equilibrium state between the two. And if it's less than 0, then B is favored thermodynamically. The energies, this Gibbs free energy is very powerful because literally, if this tells you, this difference tells you which direction things will go in. And as a matter of fact, that's how phase diagrams are built. You would say, okay, if I'm talking about going from solid to liquid, I can have a free energy here, get a G here, and the difference between them tells us which is better. I mean, I can define a Gibbs free energy of liquid here. I can define a Gibbs free energy of solid here, and it'll tell me that Gibbs free energy of solid is going to solid is negative here. That's why everywhere here it becomes solid, because the Gibbs free energy change compared to everything else goes towards solid. Same thing with here. And that's how the boundaries are defined as well. So what you would do is you would define as, if we call this line 1 here, and line 2 here, we would say that the Gibbs free energy at section 1 as a function of temperature and pressure equals the difference between, let's say, solid at a certain temperature and pressure and the liquid at a certain temperature and pressure. And this line is at all these temperatures and pressures, this whole map here equals 0. So we're drawing, we're solving this equation, and we're showing everywhere where the Gibbs free energy change of going from liquid to solid is 0. It occurs at for each temperature and pressure. This is where it equals 0. Oh, let me label what these are. This is the triple point, where you have that's where you have solid, liquid, and vapor stable. And this is where it's kind of like a new phase where you can't tell. There's no longer a distinction between liquid and vapor. It's just high energy critical phase, supercritical phase, where it's pretty much a mixture of both of them. Okay, so, and similarly with the second borderline here, it's telling you that if we define this Gibbs free energy change between solid and liquid, solid and vapor in this case, it'll be G liquid at a certain temperature and pressure minus G vapor at a certain temperature and pressure. This line traces where that difference equals 0. So that's how you would build the phase diagram. Is that for a certain temperature and pressure, like let's say we're in here at this temperature, at this pressure, the difference between liquid and vapor, that is if we say we're going towards vapor, if that's negative, that's negative, that's why it's always in the vapor phase. Same with solid and vapor. That delta G is negative, that's why it's always in the vapor phase here. When you go to a different temperature and pressure, eventually you're going to have a different relative Gibbs free energy, and this is where it's negative, 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 then it equals 0, some boundary line, then here it equals positive, meaning it goes away from vapor to liquid. So that's the thermodynamic balance that's being used to define all of this. Okay, and for a given composition, so let's say go ahead and start with the binary mixture then. So starting with the binary mixture, I'll do it over here, I guess. We can do an analysis of, graphically in terms of, let's say this is A and B. Some phase A, some phase B, or some molecule A, some molecule B. The mole fraction of B would go from 0 to 1 in this mixture. So if you're on this end, it's pure B molecules in the mixture, and at x equals 0, then it's only A in the mixture, and everywhere in between, it's A and B, which of course, if there's two of them, the mole fraction of A is 1 minus the mole fraction of B. So this defines the whole range. This defines both of them because they're coupled. So if we drew the Gibbs free energy curve, whether as a function of the mixture, many times the Gibbs free energy of the mixture, depends on the concentration of each component. So it would be equals XB GB plus XA GA. That's the Gibbs, it's the weighted average of each component times its mole fraction is the mixture. So we're saying if we start at the pure only A, it takes on this level, and if we're going to only B, it ends up at that level. But many times it's not a straight line through there. There's some optimum where, depending on what the concentration is and the temperature and pressure, of course, you'll have some curve like this. So this would be the enthalpy at a certain temperature and pressure fixed. If you have a pure component, this is the free energy. If you have a pure component of B, this is the free energy. But somewhere in between, it's a mixture, and you can find the energy, you can find, this tells you something, because another definition of equilibrium has to do with where these energies balance. So if we're saying it's a balance between enthalpy and entropy, if you find where they're perfectly balanced, that will give you an equilibrium. So another way, another criterion for defining equilibrium, so the equilibrium composition or concentrations for a binary mixture is given by where dg of the mixture by dx equals 0. And graphically, it's where the slope of this function changes direction. You know, we have to find this local optimum, local minimum. This is the local minimum here. And this is the some optimum, meaning either minimum or maximum. So what that'll tell you, by graphically finding where that is, you can find that the position where that happens is a certain concentration. So this is, for a given temperature and pressure, based on the shape of this plot, the equilibrium concentration where things are a border between one situation and the other situation happens at this particular concentration. So that's another application of the Gibbs free energy. So this map of various temperatures and pressures and then analyzing the Gibbs free energy is how these phase diagrams are built. So let's talk more about this in terms of binary mixtures. And in materials and alloys specifically, there can be some very complex thermodynamics, Gibbs free energy relationships between even just a binary mixture. So for example, steel, a simple way to describe steel would be that it's a mixture between iron and carbon, which is, it's true, that's what makes steel steel, is the carbon in there, but now we know nowadays there's many different alloys of steel that have different components besides carbon and iron. But even if you simplify it down just to iron and carbon, depending on the pressure and the temperature, you can build a phase diagram. And what has been shown experimentally, and over the years it was experiments, and then little by little we were able to understand this theoretically, it's that even just iron and carbon can have a very complex phase diagram, because there's different phases of solids, different phases of liquids, different phases of solids and liquids, all depending on the range of pressures and temperatures. So that's one example of a binary alloy that's very complex. We'll talk about two relatively simple ones today to get a feel for this. Okay, so let's talk about binary mixtures. I'll erase this up here. It's going to be another phase diagram, but specifically for a binary mixture where you don't have to worry about solubility limits. As you may remember, you can dissolve a solid powder into a liquid. You can dissolve two liquids together. But if you have oil and water, they don't mix. Their interaction between those two fluids, those two liquids, is not good, so they separate themselves out because of the molecules. One is polar, one is not polar. So that's why they don't mix. And that's called solubility. And metals behave the same way. Molten metals and solid metals, sometimes they don't form this nice solid solution. So in a simple case would be if you had two metals to make an alloy, and if they had unlimited solubility, you don't have to worry about any mixing problems. And we're talking about solid and liquid. S and L, meaning that depending on the temperature and pressure, you would have a solid or liquid. So in this exercise, we're going to be only considering, we're going to keep the pressure constant and see how the temperature affects things. So let's say that for this binary mixture, we had a range of temperatures. So starting from the hottest temperature, hottest temperature, T1, hottest meaning that both components are liquid. Because as our intuition says, if you get hot enough, everything will melt, especially metals. We're at the temperature where both of these components, A and B, are liquid. And we can draw the Gibbs free energy profile. And what that would look like is that you have, as a function of one of the components is binary. So if you know one mole fraction, you know that the other one is the balance. So from 0 to 1, we'll draw the Gibbs free energy profile like we did there. And if they're both liquid, what that means is if you have pure A here, that the GA of the solid is this number, and then we can pick another value over here for the liquid at 100%. I mean for the other component, GB, let's say that this is the Gibbs free energy of the 100% of this component at the solid. And there's going to be some optimum in between there, but it's going to be a profile that looks like this, say. And then, because the temperature is hot enough that they're all liquid, what that means graphically is that even if you had anywhere between a pure liquid of A and a pure liquid of B, everywhere between this domain, the Gibbs free energy would go towards liquid. So I'll show you what I mean by that. So this is the Gibbs free energy of the solid of the pure, Gibbs free energy of the liquid of the pure. So anything in between is a solid of the mixture. Anything in between here is the G, the energy of the liquid of the mixture. So graphically, if the temperature is high enough, there's always going to be liquid. So graphically, this is what it looks like. But if we apply this Gibbs free energy, if we define it to say that the final state is liquid, so the Gibbs free energy is lower. So this lower value minus the bigger value is going to give you favoring the final value. So that's what we're saying here. That's how it would look in the graph. If it's hot, if liquid is favored, that's because the temperature is high enough. That's how this would look in the graph. And what we're going to do is show different situations depending on the temperature, how that corresponds to this Gibbs free energy change. So if we had a situation where the temperature was decreased slightly, so let's say T2 given given that to start with, the melting point of A is hotter than the melting point of B. That's one thing. And then we can say that let's go to the melting point. Let's say now, let's draw a diagram where we say it's lowering the temperature. So T2, we're going to go to a lower temperature, but T2 is going to be the melting point of A. And that plot would look like this for Gibbs free energy as a function of composition from 0 to 1. What that means is if we're at the melting point of A, if this is a 0% B means 100% A, what that means is that if you were to draw the solid Gibbs free energy at this temperature and pressure, it'll look something like this. The exact shape doesn't matter except for this end, as we'll talk about. So this point would be the Gibbs free energy of B, because it's pure B here on this map, of the solid. This would be the Gibbs free energy of the mixture of the solid. This would be the Gibbs free energy of A of the solid, pure A. And if we're at the melting point, what it means is, as we drew for that phase diagram, is if we define the process as going from liquid to solid, the boundary line is where the Gibbs free energy equals 0. That's how the melting point is defined. It's some phase change where both are not stable, or if you stay there, there's going to be some transition from one phase to the other. So that's what this means, is that if we were to draw this liquid line, they're the same. So it'll look something like this. So this would be the Gibbs free energy of the liquid for the mixture, depending on the components, proportions. And then this is pure B of the liquid. So this is equals GA of the liquid. So that's how that would look. And, okay, so moving on to lowering the temperature a little bit more. Okay, so this is working out so far. I'm going to be able to keep that. And G mixture is the weighted average of the components. This is a pure side. This is a pure side of here. And anywhere in between is the weighted average. And this next temperature is going to be somewhere in between the melting point of A and the melting point of B. So that's T3. So T2 is T melting of A, and that's going to be greater than T3, which is greater than T2 of T melting of B. So we're somewhere in between the melting points, and let's say that this line is that it? Yeah, so let's say that this is going to be the liquid. This is GB, pure liquid of B. And if we're talking about a phase change between two solids, what happens is that these lines cross path. That on this side, the actual phase change is favored towards solid now. So somewhere in between, there's a crossover. So this is the GA of the solid. This is the GB of the solid. So here's a point where we have two different equilibrium mixtures. We said before that this is the equilibrium concentration of a liquid. And if this is the solid line, this is the equilibrium concentration of the solid, E solid, this will be E liquid. And so that's a specific case. And then, so that's basically giving us some boundaries. And what's happening here is that this is the equilibrium concentration of the solid. This is the equilibrium concentration of the liquid. The question is, what happens on this side and what happens on this side? Well, what happens is that because of this the stability between, there's three things happening. You have the phase change between liquid and solid, and you also have a dependence on that equilibrium on the concentrations and on the temperature. So we found a temperature in between the two melting points, and graphically this will be happening, and what we're doing is actually making new boundaries. So because this is equilibrium between solid, on this side everything will be solid, but on this side, if you have at the same temperature more B, because we're not at the melting point yet, you have liquid, and in between here, it's a combination. This is where you'll have solid plus liquid. So you've passed the freezing point. It's a melting point going high temperature. We're going from high temperature to low temperature. So what we did is we froze the liquid at a pure level. The liquid is not favored anymore. So now this is a frozen solid. So if you don't have enough, at some point, you're going to add more and more B from this pure A, and it's not enough to take it into the liquid phase. So this is all solid here at some concentration of B. Then due to this equilibrium behavior, you're going to have a different situation, and it happens to be a combination of solid and liquid that's thermodynamically stable. Then if you have enough B, the energy is going to favor again the liquid. Because here, liquid, if you have pure B, liquid is favored at this temperature because you're not at the freezing point of B yet. But you need to have enough B to make that happen. If you're somewhere in between, then you're somewhere in between these two phases. So that's an interesting case. And if you're at if you go lower and you eventually reach the freezing point of B or the melting point of B, depending on which direction you're going. In this case, we're going from hot to cold, so we're going to freeze liquid into solid. And the phase diagram for that looks like this, similar to this, where GB of the solid equals GB of the liquid. That's what solid point, freezing point, melting point is when these Gibbs free energies equal for the phase change. And this would be T4, the fourth temperature, equals T melting point of B. Okay, so what we did is not a phase diagram in terms of a traditional phase diagram. They can be considered phase diagrams because we're talking about the thermodynamic stability in terms of G. That is one way of doing it. But we can collect all of these graphical conclusions and balances in the thermodynamics, and when you put them all together, you can draw a line where delta G equals 0. So here delta G equals 0, here delta G equals 0, and then everywhere in between there's some combination of concentrations and temperatures and pressures where delta G equals 0. That's what a phase diagram is. So putting that together, when you don't have solubility limitations, it looks like this. So we're going to draw the x-axis in terms of mole fraction of B, and that is we can use this current scale to show some features. So if this is the mole fraction of B in this binary mixture. So this is the x-axis, but we're not going to talk in terms of G anymore. We're going to collapse these all in terms of temperature. And we talked about 4 different temperature ranges. So T2 would be where the melting point of one of them is. T3 is somewhere in between. T4 is the melting point of at the coldest temperature. So T2 would be the melting point of one of them, and that's for a pure phase. It'll look like this, where delta G equals 0, and T4 for the pure phase, it's where delta G equals 0. And what this tells us is that it's a freezing point or a melting point, depending if you go higher or lower temperature. So this is T4. And we can draw a line here. So everywhere in between here, we're going to assume this curve, which always has a curve to some extent. So anywhere below this line, we favor the solid. But the thing is, as we found out, that due to these differing melting points, that if you go to somewhere in between there, it's going to be a mixture. But if we're at T1, then at T1 everything is going to be hot, everything is going to be liquid. So we didn't find a way to find this liquidus line, but what we have here is going to be 3 different regions where everything below this line is a solid. Everything above this temperature is a liquid. But depending on your concentrations and depending on the specific temperature, there's some region bounded by these 2 lines where you can have a solid plus liquid. So this is called, these 2 lines have specific names. If you have this behavior between 2 different metals or 2 different components and they have differing melting points, it's not because of some solubility issue, it's because of the melting point difference. You can have a combination of the 2 which is stable, thermodynamically stable, and this line is called the liquidus, where everything above it in terms of temperature is liquid, and this is the solidus line, where everything below this line in terms of temperature and at the fixed pressure is frozen, is solid. And again, this is all for a fixed pressure. All of these lines shift depending on the pressure you are at. Okay, so that's how we build this particular phase diagram for a binary alloy when you don't have any limitations on mixing them together. Any energy that's stable when they're always mixed together. There's no pressure or temperature which affects their how they can mix. This is assuming that it's a solid solution where they're uniformly distributed. We're assuming this is a liquid solution where they're uniformly distributed. And we assume that this is a mixture phases where they're uniformly distributed when there's no limitations of the solubility. So thermodynamics also assumes, pretty much one way to think about it is that everything is slow enough that this equilibrium can be reached. That takes time to uniformly distribute the energy, and if you do it too fast, you're not going to reach equilibrium if things happen so fast. So what this diagram assumes is that whenever you change one temperature and pressure to the other temperature and pressure to the other concentrations, that you're at equilibrium, and in real life, that takes time to reach that state. So that's another thing about these diagrams is you have to assume that you are in equilibrium to begin with, which eventually gets reached. I mean, for liquids and gases, eventually that gets reached, but for solids, sometimes an unstable state thermodynamically stays that way because the transition to stable state is so slow because solids take so much time to change by themselves by thermodynamic driven forces. At high temperatures maybe, but the mobility, the ability to change the atoms, the mobility of them is much harder, much slower in solids, where you can reach these so-called metastable states that are not favored thermodynamically, but because you froze them before they can reach equilibrium, it pretty much ends up staying like that. So that's not a phase, that you can find phases that are not in the phase diagram at a certain temperature and pressure, and one reason that could be is because it got frozen, literally frozen, before it can reach equilibrium to its thermodynamic state, and many times it stays that way for the foreseeable future in terms of the application or in terms of our lifetime. Okay, so let's move on to a more complex situation, which we will not build slowly, but we're gonna, it's a very common situation. Okay, so another case is, they're called eutectic binary alloys. Eutectic is a, I guess a scientific word, but it comes from, I guess back in the day, they observed this, that if you have two different alloys, each of them has their melting temperature. It's interesting what happens if you mix them, depending on what you're mixing, that in some cases, it's called eutectic because when you mix them together, it's actually easier to melt than them individual components. That's why it's called eutectic. That's where the word eutectic means. And the reason why it has an interesting phase diagram is because of insolubility at some point. Another word for insolubility is miscibility. The miscibility is good, it's soluble. So miscibility limitations. And Thermodynamically, one way to say that is the mixing energy, mixing enthalpy is much greater than 0, meaning it's not favored to mix. So this causes more complex phase diagrams, more complex behavior. And I'll just go ahead and draw what that phase diagram would look like. So at a certain range of temperatures, at a range of binary mixtures from 0 to 1, you would have many features. So this would be temperature. So let's define this temperature here to help me draw this out. So what happens is you have much more phases, basically. So this will be one boundary. This will be another boundary. So at low concentration of B, high concentration of B, and then you'll have a boundary here. So what happens is, due to this miscibility, somewhere in this moderate range of one component, you'll have a mixture of solid. So this will be solid. Wow, dead. Solid A plus solid B. You'll have two different solids, solid solution here. But if the concentration of B is high enough, only solid B would be happy. Similar here, only solid A is happy here. This is where this miscibility comes in. And then on top, it's going to look something like this behavior here. But because of the mixing problem, it's more complex, where let's say here, so that's another line for reference, where at this temperature you have a transition where this is where the solid liquid stability is for this combination of, let's say, some solid B plus liquid mixture. And then here, similar, this is where solid A is happy with the liquid, and then everything above here is liquid. So this also has these solidus and liquidus. So here, this line here, I'll draw the line in orange. That's the solidus. Anything below that is solid. And here, everything above this line, that's the liquidus. And in between is in between. So the eutectic point is this. It's where three phases are stable. Alpha A plus alpha B plus the liquid are all stable here. And it's eutectic. It's not the triple point, it's a eutectic point because it has to do with the melting point. And as we see, what's interesting is that this is the melting point of A. This is the melting point of B, meaning temperature. And if you mix them together, it's even easier for it to melt. That's what the word eutectic means. So that's interesting. And that's what you see on this phase diagram. You're literally melting. If you start at a colder temperature and you increase the temperature, you'll reach a boundary between solid and liquid. That boundary is the melting point. So this would be eutectic temperature. So so the eutectic point is both a temperature and a concentration. So it's a, T XA XB is the point. That's the coordinates. And if it's binary, then if you know B, you know A. So that's one thing. It's like it's from the same principles of these, but if you have some extra limitation of the energy, the stability of mixing, this can happen. And so the next thing would be that you can use these principles along with the principle of phase change. And the way that would work, I mean, one way to investigate that would be to use the principle that when you're putting energy into a system or you're taking energy out of the system, in terms of temperature, you can think of that increase in temperature or decrease in the temperature, heating or cooling. Whenever you reach these boundaries where the phase changes, as we should remember, the temperature does not change during that transition of phases. That energy goes in or out of changing the phase. So instead of changing the internal energy, the enthalpy, the temperature of the system, you change the phase of the system and the temperature stays the same. So you can use that principle to probe into what is going on. So we can do 3 different experiments or 2 different extremes. So let's say that we're at this concentration. We have an alloy, binary alloy, at this concentration of B, which fixes the concentration of A. So this is where we are on this phase diagram. And then let's start at this temperature of liquid. Let's melt it and then let it cool. At the same mixture, it's going to keep the same proportions. It's just going to decrease in energy, which will decrease the temperature. And we can make a cooling curve. So for A, what did I call this? 1. So we'll do cooling and heating curves. So cooling, heating curves, it's mostly done with cooling because it's easier to work with, are the temperature response with time, basically, for a given concentration. And what you do is you use this because phase change temperature and time give clues for phase and composition and concentration. So you can use a response, you can measure starting from a certain temperature, ending at a certain temperature. You can look at the profile in time to see what happens and use that as a marker. So if you do this here, let's call this 3, starting from here and going all the way down. So start at this composition. Let's say that this is composition of 1. This is a composition of B3. We have this proportion of A and B, 2 different mixtures, and we cool them down. Because they're going through, what they go through is starting at the pure liquid phase, they decrease temperature, then they reach a boundary where some of the liquid solidifies to solid. Some of the A comes out as a solid. Then you keep on decreasing the temperature, and then both the A and the B freeze to solid. So there's 2 different phase changes going on. It's pure liquid, then some of the solid, you go to one transition from liquid to solid. Some of the liquid is still there, some of the liquid is there. Then all the liquid, the remaining liquid goes to solid. And you have a second phase change. And because the concept of latent heat of phase change, the temperature stays constant. So for the cooling curve for situation 2 and situation 3 would look like this, where you start off at the high temperature, then with time, if you let it cool, if you let it equilibrate with its cooler surroundings, the temperature is going to decrease, but then you're going to reach a certain, the liquidus line. T liquidus. For a certain composition, it changes. So this would be for this mixture, the temperature that meets the liquidus line. And once you hit that, the phase change is going to happen, and the temperature will stay constant until that phase change is over. So it's going to take some time for all that liquid to freeze into A over some time. It depends on the mass and things like that. So this would be the liquidus. This would be one region. Then when that is over, you'll go back into this a region where you can cool down. The temperature will change again until you go through the second phase change of both going to solid. And then when both are solid, the temperature will decrease again. So this would be a liquidus line, and this would be the solidus line. And that will give you a clue, because this liquidus line depends on temperature and concentration. So if you say that this is 300 Kelvin, like 600 Kelvin or something, then if you look at the phase diagram and everything's at equilibrium, you can say that if the liquidus line is observed at 600 Kelvin, then that means my concentration is this amount. So that gives you a clue as to the composition. You can kind of back out the composition depending on the temperature, and you can do that again with the solidus, which is, if that's flat, then that's less constraining on the conclusion you can make. But if you go, okay, so that's one way to use the cooling curve, because you would expect to see phase change when you have some transition from all liquid to some solid. Then you go from a mixture of solid and liquid to all solid. Those are the transition from liquid across the liquidus going to a mixture across the solidus. Those are two different phase changes. And because of the concept of latent enthalpy of phase transition, the temperature stays constant because the energy is going into or out of phase change. So let's look at the eutectic point. So if we say some cooling curve 2 is for a different mixture, it's a different proportion of A and B, which we'll say that it's at the eutectic, because at that proportion of A and B, it has this triple point here, and there's only one phase change from pure liquid to pure solid. So it'll be more simple in that respect. So that would be the eutectic phase change, and with a specific temperature. So these cooling curves, depending on where it's flat, will tell you what temperature the phase change occurs, and the temperature that the phase change occurs can be traced to the composition that corresponds to the phase diagram. So stuff like that. That's how you can graphically use these phase diagrams and get some insights into the behavior of these materials. Okay, so that's all I had today. Thank you, and I'll see you guys next time.